Welcome to Spring LIB.
So in this problem, we're going to be talking about the thermite reaction. The thermite reaction is really cool because you take iron 3 oxide, which is a solid, you react that with aluminum metal, which is also a solid, and it creates aluminum oxide and liquid, which is a solid, and liquid iron. How cool is that? So this reaction generates so much heat that our iron is going to be a liquid, that our iron metal is going to be liquid. So our first step here, we want to balance this equation. So when we're balancing equations, remember that we want equal numbers of each type of element on either side. So I like to start with metals and then remember to leave your oxygens and hydrogens for later. How I remember this is you do all of your other metals and then you say, oh, I forgot the last two. So you can remember your oxygens and hydrogens are last. So let's start. We have 2 irons on this side. We need 2 irons on this side. We have 1 aluminum on this side. We have 2 aluminums over here. So now that all the other metals are balanced, we have 3 oxygens, so we need 1 of our iron oxide and 1 of our aluminum oxide balanced. Cool. So our next step is we need to calculate the number of grams of aluminum needed to completely react 500.0 grams of our iron 3 oxide. Okay. So in order to do this, we need to remember our dimensional analysis. So to do dimensional analysis, we are going to think about where we're starting and where we need to go. So we're starting with grams of iron oxide, and we want to end up with grams of aluminum metal. So how do we get from here to here? So we can go from grams to moles of iron oxide. We can do our stoich to be able to compare our iron oxide with our aluminum. And then from our stoich, we can go to moles of aluminum and then to grams of aluminum. So here's our process. So let's get started. We have 500 grams, 500.0 grams of iron 3 oxide. We're going to multiply that by the molecular weight of our iron 3 oxide, which I have calculated as 159.69 grams to 1 mole of our iron oxide. And then we're going to do our stoichiometry step. Let's scroll back up to our equation. We have 1 iron 3 oxide for 2 moles of aluminum. So we have 1 mole of iron oxide to 2 moles of aluminum. We have 1 mole of aluminum. The molecular weight of aluminum is 26.98 grams. So this will give us an answer of 168.95 grams of aluminum metal to completely react with 500 grams of our iron 3 oxide. Okay, so our next step here, we're given that the reaction produces 852 kilojoules of heat per 1 mole of our iron 3 oxide. So how many grams of iron 3 oxide is needed to produce 1 times 10 to the 4th kilojoules of heat? So we're given that we have 852 kilojoules per 1 mole of our iron 3 oxide, So we want to go from heat to grams. How are we going to do that? So we're given a conversion factor here. So we're able to go from heat to moles. and we can go from moles to grams. So this one is going to be pretty simple here. So we have that we want to generate 1.00 times 10 to the fourth kilojoules of heat. We know that we generate 852 kilojoules of heat per 1 mole of our iron 3 oxide. The molecular weight of our iron 3 oxide is 159.69 grams, which will give us a final answer of 1,874.3 grams of iron 3 oxide needed to generate 1 times 10 to the fourth kilojoules of heat. Okay, so for our final part here, we are wondering if you perform the reverse reaction. So let's look at our reaction here again. This reaction here. If we perform the reverse reaction, so this arrow will now be pointing this way, will heat be a reactant or a product? So let's think a little bit conceptually. So remember, this reaction here generates so much heat that our iron metal is a liquid. So what does that mean for our reaction? That means that one of the products of this reaction is heat, because when these two metals react with each other, you are generating so much heat that the iron here will be a liquid. Therefore, heat will be a part of the products. So in order for this reaction to run in reverse, you're going to need an input of energy here.